Hello everyone and welcome back to another mini concept, this time about entropy and Gibbs free energy. So these are the next steps above enthalpy, and Gibbs free energy is actually where everything comes together. So enthalpy, entropy, they come together in Gibbs free energy. So first let's describe entropy and Gibbs free energy. So entropy is the measure of disorder of a system as well as the tendency of a reaction to happen, while Gibbs free energy describes the spontaneity or how likely a reaction would happen by itself based on the enthalpy and entropy of a system. So, how do we understand entropy? Let's start there first. So, entropy is basically the likelihood that this a system will fall into disorder. Now, what does that mean? Disorder is really a loose term. Rather, imagine a imagine a ball rolling down a hill. So the natural tendency of a ball starting from the top would be to roll down the hill, and it's not exactly disorder, but rather it's moving towards its natural tendency, which is to follow gravity. And when reactions follow their natural tendency, that means that they're going towards the natural flow of things, right? And high entropy means that the system is disordered enough that it would likely happen. And this is as opposed to low entropy, which is basically when it's ordered. So if something is ordered, then it would not likely follow a tendency such as falling down, or a tendency for anything to fall into chaos. So how would that look like in the context of a ball? In the context of a ball, it would be like, instead of allowing the ball to roll down, you're controlling the ball on the way up. So let's say that this is a ball and you're the person trying to push it all the way up a hill. You're controlling your push of the ball upward, and you're moving it away from the natural tendency of it to roll down. Essentially, you are making the ball ordered. Now, how does this work in reactions? Okay, so how about the take into consideration a simple combustion reaction. Let's say a simple combustion reaction. So let's just say we have A plus oxygen gas combusts into carbon dioxide and water. Now, when we apply the oxygen and we make it combust, the natural tendency of this system would be to form these products, right? And if this system has a positive entropy, that means it's likely to form these products. It's likely that the reaction is going to happen, or it's going towards, well, its end goal. Now, how about if it's negative? If the entropy is negative, then it's not very likely that it would fall into disorder, or it would essentially just stay how it is right now. And that's, of course, without the addition of the consideration of enthalpy. But that's essentially the general gist of entropy. Now, how do we solve for entropy? Well, to solve for entropy is very similar to how we solve for enthalpy. So, as we can recall, enthalpy was solved using the following formula. So, we have total enthalpy delta H is equal to the summation of the enthalpies of formation of the products minus the summation of the enthalpy of formation of reactants. Now, this is basically the exact same thing for entropy, except instead of having it as H, it becomes S. S is the symbol for entropy. So before we go here, before we get to this part of the solving, we need to understand also the computation of entropy with regards to the system itself. So like the nature of a system. Let's bring back the box example. So let's say that we have a box and this is a closed system, right? And around the box there is a surrounding. So surrounding is here. This is our system. And in general, around the surroundings is just nothing. Let's say that it's nothing. When you add the surrounding and the system, that's what we call the universe. Now, we don't mean exactly by the universe as in literally every galaxy and atom and whatever there is nearby or that ever existed. No, instead, we're just talking about a system and its immediate surroundings. Or, of course, depending on the context. For example, let's say we have a shoebox and our system is the shoe. The surroundings of the shoe, which is the air, would be our surrounding, and our universe would be the shoebox. Now, how does the entropy, what are the calculations or the quantifications of entropy with regards to this type of system or this systematic consideration? Well, simply put, the entropy of the universe has to be equal to the addition of the surroundings entropy and the system's entropy, because it's impossible that there would be any difference, because energy cannot be created nor destroyed, and in that same way it has the entropy and the energy of a system must be constant. So the entropy of the universe would be equal to the entropy of the surroundings plus the entropy of the system. Now, how about when we're going through equilibrium? Let's say that everything is perfectly fine. Like there's no heat transfer, there's no addition of other matter, or essentially there's just no disorder. Everything's on equilibrium. So the addition of these two, the surrounding and the system, would equal 0 in equilibrium. So this is the entropy of the universe at equilibrium. So that would be equal to 0. Okay, so well, now that we have that consideration, we can try a simple, really quick example on how to get the entropy of the universe. So the entropy of the universe, let's say that our surroundings has an entropy of 10 joules per mole Kelvin, and our system has 100 joules per mole Kelvin. Okay, that is not good handwriting, but basically, yeah, 100 here, 100 there. Now, to get the entropy of the universe, we just have to add them. So 100 plus 10, that's 110 joules per mole Kelvin. And that's how you get the entropy of the universe. Alright, so that's it. Now let's move forward to understanding entropy in computational context. So entropy also has, well, the entropy of formation. And the standard entropy of formation of these whatever reactants or products that you have are all standardized as well, similar to enthalpy. So you can find them in sources online or maybe in a textbook. And just like here in this question, we have them given to us. So we can actually give this a shot immediately. To get the entropy of this problem, all we have to do is plug and play the quantities given. So hold on, let's change the color. So the entropy would be equal to the summation of the entropies of the products. Now, what are our products here? We have nitrogen dioxide, and we have Cl and O. So for here, we have to identify the entropy values of our products first. So the entropy value for nitrogen dioxide is 240.1 joule per mole Kelvin. So we write that down first. So 240.1. And we're going to add the entropy of Cl and O. So that's that is 261.58. And then we're going to subtract the entropies of the reactants, and that's minus 272.23 plus 210.8. Now, if we solve this, we're going to get an answer of, hold on, let me get my calculator, 240.1 plus 261.58, subtracting 272.23 plus 210.8, we would get an answer of 18.65 joule per mole Kelvin. 18.65 joules per mole Kelvin. So that is our total entropy for the reaction. Now, let's move forward and add a bit more to our understanding of entropy. Let's bring this down here. Okay, so entropy also is related to enthalpy. How so? Well, enthalpy allows us to measure the entropy change within the surroundings. So, whenever a system loses heat, going back to enthalpy, whenever a system loses heat, the surroundings gain the energy that's lost by the system. So, the relation of enthalpy within for a system and its surroundings is negative. The negative enthalpy of a system would be equal to the positive enthalpy of the surroundings, or the positive enthalpy of the system would be equal to the negative enthalpy of the surroundings. Now, this isn't necessarily true for entropy, however. In some cases it is, but for entropy, it follows the second law of thermodynamics, which is that the total entropy of a system or a universe would be equal to the entropy of the surroundings plus the entropy of the system, which is going to be greater than 0 if we're going to be able to have a reaction continue, or essentially push through naturally. Now, that said, how would we be able to measure the change of the entropy of the surroundings, given that we may normally be able to calculate for the entropy of a system, but not always the entropy of the surroundings? And more than that, we also sometimes may not even be given the complete entropy of the system, but rather just the enthalpy. Well, to get the change in entropy of the surroundings, we follow another equation, which is the negative change in enthalpy of the system divided by the temperature is equal to the change in entropy of the surroundings. So let's say that we have a system that has 40 joules of energy, and our temperature is in Kelvin, let's say 300 degrees Kelvin. So this is multiplied by -1 because it's negative. Now we would cancel this out. This is just 4. This would be 30. We can cancel this out even more. This would be 2 and then 15. So it would be -2 over 15. And that would be in the units of... Hold on. That would be in the units of joule per mole Kelvin, and that would be the entropy change for the surroundings. So that's essentially how you're going to get the entropy change for surroundings using only the enthalpy of the system. Anyway, back to our primary discussion on just general entropy. Now, for this next part, we're going to skip over the enthalpy portion because I already have the answer for that and I'm going to write it down now. So the answer to question B was the enthalpy of the reaction is negative 17.86 joules or no kilojoules per mole. Okay. Now, our last question here for this one is asking about Gibbs free energy. Now, what is Gibbs free energy? Well, like I mentioned here in the beginning of this video, Gibbs free energy describes the spontaneity of any reaction. But what actually is Gibbs free energy? Well, from the name itself, it's free energy. When something is free in the context of chemistry, it means open for use. Whenever we have extra energy, that means it hasn't been used yet. That means it's still expendable. Right? Now, when we're lacking free energy or we have negative free energy, that means there's nothing left to be used or to keep the reaction stable. Essentially, it's going to follow the natural course of things. Now, Gibbs free energy is interpretable in terms of spontaneity compared to disorderliness. So, whereas entropy, whenever it's greater than 0, we can just say that it's product favored, and when it's less than 0, it's the opposite, reactant favored. Whenever we have Gibbs free energy that is greater, so Gibbs free energy that is greater than 0, this is non-spontaneous. And whenever we have Gibbs free energy less than 0, this is spontaneous. So let's put this in a different color. And again, how we explain this is because whenever we have extra energy to cling onto, it's not going to, you can't really just lose the free energy. You need like an extra push. You need another way to make sure that the system cannot hold on to that amount of energy anymore, and it has to shift. It needs to follow the course of the reaction. And whenever it's negative or it has a lack or a decrease in its Gibbs free energy, or just in general the free energy, then that means that it can't cling on to anything anymore and it has to follow the natural course of things. And the natural course of things would be dictated, of course, by the reaction. And we can actually start to see where entropy comes into play here. Because I keep mentioning the natural course of things, and whenever a reaction happens, it has to follow the correct direction of the equation, right? And a spontaneous reaction means that it would naturally follow the natural course of the equation given a certain temperature, given certain conditions. Non-spontaneous, basically the same thing, except this time it doesn't happen. Now, there is a formula for Gibbs free energy, which combines enthalpy as well as entropy. So Gibbs free energy is given by, hold on, let's change our font color, let's use this one. So Gibbs free energy is given by the enthalpy minus the temperature times our entropy. So from here, we can actually start to analyze how this equation makes sense. So we know that, well, okay, let's put some subscripts here. These are all of the system. Okay, so we know a while ago that the energy change of a system is given by the enthalpy, and the disorderly change of a of a system is given by, well, our computations earlier. Whenever we take into consideration this equation, we're actually able to arrive at an answer that describes the overall usable energy of the entire system or the entire equation, right? And we can actually give this a shot right now. So our enthalpy here was negative 17.86 kilojoules. Well, that's in kilojoules, and our entropy a while ago was in joules. So we're going to multiply this by 1000, which would just give us negative 17,860 kilojoules. And we're going to subtract times standard state, which is 25 degrees Celsius, which needs to be in Kelvin, so we add 273. We multiply it by our entropy, which was 18.65. Now, if we put this into our calculator, we should be able to get an answer of equal to about negative negative 23,417 joules per mole. So, what does this mean? Well, we start first by interpreting based on the sign, and we can see that the sign here is negative, so that means that there is no more no more free energy for our reaction to cling onto, and it has to go through with the reaction based on its natural course. And this brings us to another way to interpret Gibbs free energy, which is based on the sign again, but this time we have different names for it. In enthalpy, we have, for positive signs, endothermic, while when it's negative, we have exothermic. Same thing for Gibbs free energy, except this time for positive Gibbs free energy. So positive signs, positive Gibbs, this is what we call endergonic. Okay, that is bad handwriting. Endergonic. There. And whenever it's negative, we have, maybe you can guess already, exergonic. There. So, based on this, our reaction here, the Gibbs free energy here, the behavior of the system is endergonic in terms of Gibbs free energy. Now, for Gibbs free energy also, we didn't use it here, nor will we in our next example, but Gibbs free energy is also solvable using the same formula as entropy, which is just the change in Gibbs free energy is equal to the Gibbs free energy of formation of the products, and that's subtracting as well from there the Gibbs free energy of the reactants. So enthalpy, entropy, and Gibbs free energy share the exact same formulas, and that's specifically for whenever we're dealing with the enthalpy, entropy, and Gibbs free energy of formation. That's it. That's Gibbs free energy. Basically, it just dictates how likely it would be going to the other side by itself. So let's try another question, but this time it's going to be a bit of a manipulation of the Gibbs free energy formula. So the Gibbs free energy formula again is Gibbs free energy is equal to the total enthalpy minus the temperature times the change in entropy. So here we're given the Gibbs free energy, so that's 53.2, and then we're also given the enthalpy, which is negative 21.5, minus the entropy in joules of 14.7, which needs to be in kilojoules so that we can make sure that everything's uniform. So that's times 10 to the power of negative 3, and that's times the temperature. So now, where do we go from here? Well, one easy way to identify what to do is just the fact that we only have one variable. And since you only have one variable, That means we can algebraically manipulate our equation. So how would we do that? Well, we'll have to transpose our 21.5. So move all the way here. Negative 53.2 plus 21.5 is equal to negative 14.7 times 10 to the power negative 3 times the temperature. Now, we would also need to divide both sides by this. So, our final equation for our temperature would be negative 53.2 plus 21.5 over negative 14.7 times 10 to the power of negative 3. And this would get us a final answer of 2156 Kelvin. So that's quite large, not large, but instead really quite a high temperature. But that's it. So for this following reaction, the Gibbs free energy is negative 53.2 kilojoules whenever the enthalpy and the entropy are as follows, and the temperature is 2156 Kelvin. So that pretty much wraps up our discussion on entropy and Gibbs free energy. These aren't the easiest topics to wrap your head around. That is something I will say about entropy and Gibbs free energy. It's a bit confusing trying to rationalize something that you can't really see. Well, that applies for a lot of things in chemistry, but this one especially, because it's like, what do you mean when it's disordered? What do you mean that it can spontaneously happen? These things are abstract. However, the more we expose ourselves to the concepts of chemistry, the more we can actually understand how this makes sense. We can just do a quick recap to try and see and rationalize it again with all of our new understandings, our new learnings. Again, entropy is the measure of the disorder of a system and the tendency of a reaction to happen naturally. So, when we say naturally, we mean like towards the product or towards the reactant. In other words, the inclination of a reaction to just be, to happen, right? When something is more disordered, it wants to produce something else. And in this case, for example, in our first example, our reaction wants to change into nitrogen dioxide and ClNO from our original reactants. So whenever our entropy is positive, it's product favored because it wants to change naturally. And whenever it's less than zero or negative, that means it doesn't want to change and it wants to stay ordered. It wants to stay on the reactant side. Now, how about when we take into consideration our enthalpy and our total energy change and the disorderliness of our system? That's when we get to Gibbs free energy, because this allows us to understand how much energy there is available for us to use still in that reaction. And it dictates whether or not it's gonna happen by itself or if it's not gonna happen. And when Gibbs free energy is greater than zero or positive, it's non-spontaneous and it's not gonna happen by itself, simply because there's still a lot of energy that's left over that it hasn't expended yet. It can still cling on to it by and keep itself stable, the reaction. While whenever it's less than zero, that means that the energy is spent. The energy is already going to be, well, used up in the reaction, and it's going to happen. And that's it. That's really, that wraps up everything, and I hope you guys understood that. And if there's anything that I can do to clarify in any part of this topic, let me know in the comments so that I can be of help. But overall, that's it. And thank you everyone for watching this video. I hope you all learned something, and I'll see you all in the next video about heat capacity and specific heat. All right. So thank you everyone, and goodbye.